Next we have number 10, where an invertible function f is given whose domain is x and codomain is y. We have to then show that f has a unique inverse, that there is only one inverse. We start the solution by assuming two inverses of f, g1 and g2, both of which of course will have y as their domain and x as their codomain. So let these two functions be the inverses of f, be inverses of f. I should not say the. And what is our aim? Our aim now is to prove that g1 and g2 are equal as functions. Now next what we do, we consider any point y in y, that means the common domain of g1 and g2, and we consider this composition f of g1 of y. It makes sense because y is coming from the domain of g1, so g1 of y makes sense, and it's an element in x on which we can apply f because x is the domain of f. Okay. Now this, by the definition of composition of functions, is f composite g1 of y. This however is just y. Why? Because g1 is an inverse of f. So f composite g1 will be the identity function on the set y. So if anything is coming from y on which you apply f composite g1, nothing is going to change. That same element y will come as output. But the same can also be said about this other composite function f composite g2, because g2 is also an inverse of f. So f composite g2 is also the identity function on the set y. So this, when applied on this element of capital Y, will also not change that element, that is small y will remain small y. And this however, just like this one, is f of g2 of y. Next we note this fact that since f is invertible, that is our hypothesis, right? This is what we start the solution with. Because of this, in particular, f is also 1, 1, because being invertible, f is both 1, 1 and onto. And what did we see just now? That f of g1 of y is equal to f of g2 of y. So because f is 1, 1, from this equation we conclude this, that g1 of y is equal to g2 of y. Since f is 1, 1, so if the outputs of f for these two inputs are equal, then 1, 1ness tells us that the inputs themselves have to be equal. But what can you say from this last equation? You see that this one, what is it telling us? It's telling us that no matter what point y you choose from your set y, the outputs that g1 and g2 give you for that input y are same. So that means g1 and g2 are identical, that is they are the same function. So that's how f has only one inverse, that is the inverse of f is unique. You can write one more line for that. So there the solution ends. Let's see another one, number 11, where you have this function f with domain consisting of 1, 2 and 3 and codomain consisting of the letters a, b and c. And the rule defining the function f is this. That means these collectively give you the rule. F of 1 is a, f of 2 is b and f of 3 is c. Very straightforward. So you can at once see that this f is both 1, 1 as well as onto, and that is why it will have an inverse. So we have to find the inverse of f, and then we have to show that the inverse itself also has an inverse, and the inverse of the inverse is nothing but f itself. We of course start the solution by proposing a function that we believe should be the inverse of f. And it's easy to guess what the inverse should be. You just make the inputs outputs and outputs inputs. That means this time, and one more thing, G will have the domain which is the codomain of f, and the codomain of G will be the domain of f. Alright. F of 1 is a, So we define g of a to be 1. Similarly, g of b is 2 and g of c is 3. Now to prove that this really is the inverse of f, what are the things that we have to show? We have to show that the two compositions f composite g and g composite f are identity functions on appropriate sets. So we first concentrate on this composite function f composite g, which you already know, or you can see that it's a function from this set into itself. So let's see its effect on the elements of that set. F composite g of a is f of g of a by definition of composition. Now g of a is 1, so that's how you get f of 1. And if you recall the definition of f of 1 is a. So you get a back. A was the input and a is output also. Similarly, f composite g of b is f of g of b. G of b is 2, so that's how you get f of 2, which is b. So you again get b back. And finally, f composition g of c is f of g of c. G of c is 3 and f of 3 is c. So you are getting all the inputs as outputs. That means this function is the identity function on this set. And next we have to prove that g composite f is the identity function on this set. Actually it's the function from this set into itself. So next we have this g composite f of 1 is g of f of 1. F of 1 is a and g of a is 1. So this time we are getting 1 back. Similarly, I won't go through everything here. So you can see yourself that just like that, g composite f of 2 is 2 and g composite f of 3 is 3. So yes, just like that one was the identity function on the set a, b, c, this one is the identity function on the set 1, 2, 3. So that's it. These two things let you conclude that our function f is invertible, and not just that, the inverse of f is g. So we write the conclusion like this: hence f is invertible with f inverse equal to g. And then to show that f inverse itself is also invertible, actually what is it that we have to show? We have to show that there exists a function, say h, such that f inverse composition h is an identity function and h composition f inverse is also an identity function on appropriate sets. But we already have shown that, right? With f itself in place of h. And that is why next we write, note that the above argument also shows that this function, which is f inverse or our g, same thing, is invertible with f as its inverse. In other words, the inverse of g or f inverse is f itself. And there the solution ends.